Hi again. So today I wanted to tell something about the integral theorems. In fact, this theory relates more to calculus, but I'm not sure that you all remember these things so good, so I prefer to take some time, not very much, to remind about this integral theorem. So first is the divergence theorem. It is Gauss, Strogradsky. It is the following. Suppose we have domain D in n-dimensional space in Rn, and consider a vector field U of x, of x1, xn. It is a vector field, arbitrary, sufficiently smooth vector field, so that at least once differentiable. And we consider also the surface S, it's the boundary of D, and at every point the unit normal n, depending on x. At every point of the boundary, I consider unit normal which looks outside. Then we consider the following integral over S, divergence U dx. So divergence U is equals integral over S sum du I dxi, I from 1 to n dx. And the integral theorem says something about this integral, which will appear in the end. Now consider just one term here, integral over d, integral over s, like double integral, dui dxi dx. So suppose this is our domain, it is the coordinate system, it is the xi axis, and all other axes are beyond xi. Let me denote it by x prime. So x prime is all the axes, x1, x2, and so on, with one omitted, xi omitted. Yes, so one xi we consider specially just to find this integral. Now, suppose for simplicity that our domain is such that S has the following equation. Xi more or equal, say, phi of x prime, and less or equal, say, psi I of x prime. Yes, so we have two surfaces, say this is xi, this is all other x prime, and our surface S, it consists of two parts. This part is given by xi equal phi of x prime, and this part is xi equal psi of x prime. Yes? And each, suppose that each line parallel to, straight line parallel to axis xi meets the surface at 2 points given phi of x prime and psi of x prime. Yeah? No, if it is within some projection of this surface on the plane x prime plane. Yeah. Then we can write this integral as iterated integral. So let me denote this integral by I. I equal integral dx prime over, say, di, it is projection d on the x prime. Yes, so this is domain di. And here integral from phi I of x prime to psi I of x prime. Yeah. D ui dxi dxi. Yes. So we integrate first along these segments, and then we integrate the results over projection of all this domain on the plane spanned by the coordinate axis, all but with one excluded xi axis. But this is so integral of derivative along this segment from phi equals integral over di ui of psi of x prime psi I minus ui of phi I of x prime dx prime. Yeah? And now let us consider, I have to make some space. Again, this is our domain. Just a minute, maybe other pen is better. So this point x prime, and this is phi and psi. So consider this x prime, say x prime plus dx prime. Yeah, consider, no, let it be two dimensions, so it's xi and the other x prime. Then you have this difference times dx prime is the area of this rectangle. So it is phi of x prime, it is psi of x prime. It is No. What is written here? Let us. I wanted to have express it in terms of the area integral over the boundary. So this is the normal vector n, and consider also the unit vector ei, unit vector in the direction of xi vector. And then you can write, one moment, that this integral I equals integral over di. I'll take other different pen. Integral over di psi ui of x prime psi I of x prime, instead of dx prime, I write ds, but you have to multiply. It is ei dot n at this point. ds, it is this element of the area here. Plus ui of, just a minute, minus ui x prime phi I of x prime. Here you have this ds, but let me write ds2. And here n2, and here we have normal vector n1 and minus vector minus ei times e minus ei dot n1 ds1 here. So we can write it equals integral over d. We have minus here and minus here, so they give plus. And so what we have here, u I of x, integral, in fact we integrate over s, yeah, so integral over s, no, integral over gi, but it equals integral over s ui of x, x is x prime and xi, times ei dot n ds. After all, we have this expression, and integral over d sum d ui dxi dx I from 1 to n equals the following. We just find the sum of these integrals over all I. Integral over the surface sum ui of x ei dot n ds. But what is written, it is exactly u equals integral over s u of x dot n of x ds. So this is the integral formula. So again, I write this finally. Integral over d. D is this is d, this is s. Divergence u dx equals integral over s u dot u is vector n, it is a scalar function, ds. So this is the divergence formula or divergence theorem. So what is written here, it is called flux of vector field u of x through the surface S. Now, in deriving this formula, we used conjecture here that the lines, straight lines parallel to the axis xi have only 2 points in common with the surface S. Yes? And if the surface is more tricky, then it is not so obvious. So suppose we have this domain, it is D, it is S. So it meets some lines at 4 points, which is parallel to the xi axis. Yeah. So what to do in this case? Here we can take this surface, this domain, and we can cut it in pieces, like this. So we have pieces. Let me remove this. It is domain number 1, domain number 2, and this domain number 3. Yeah? And all together they form domain. So the theorem is true for domain number 1, and with this boundary, for domain number 2, with this boundary, and domain number 3. And now let's observe that if you take the sum of the left-hand sides integral of divergence u, divergence u is a scalar function, so the sum of integrals over these subdomains d1, d2, and d3 is exactly integral over the union over domain D. And about the right hand side, we have the flux through, say, the boundary of D1. It is this surface. Let me. Yes. Includes the flux through this part, external part. So it is S1 prime, and internal prime part, S1 double prime, which is a piece of boundary between D1 and D3. The same for D2. Here it is, its boundary is union of S2 prime and of S2 double prime. And the same for D3. So D3, its boundary is here. Here is the piece S3 prime, and here the piece S3 double prime. Yes? And you see that integral over S1 is the sum of flux through S1, is the sum of flux through S1 prime and S1 double prime. The same for S2 and S3. And now you can see that the flux through S1 double prime is exactly opposite to the this piece of the flux through this piece of S3 prime, this piece, because here the unit normal vector is external vector, so from this domain it looks outside, and from this domain it looks in the opposite direction. These are two, this is normal vector to this piece of boundary which looks outside of D1, and this is which looks outside of D3. And so corresponding pieces of this integral of this flux are opposite to one another, so they cancel. The same happens here. So these two fluxes through S1 double prime and S2 double prime exactly cancel the flux through S3 double prime, because here the same vector field, but we consider how its flux with the opposite normal vector. Yes? So this means that contribution of this internal surfaces, of cutting surfaces to this integral exactly cancel, and what remains is just contribution through this piece, and this piece, S1 prime, S2 prime, and S3 prime. So this means that this theorem, if it was true for each piece, remains true for the whole domain. Similarly, we can consider, say, domain like this, which has a cavity inside. So this is our domain D. So how can you treat this domain? You cut it into 4 pieces. Yes, so it is D1, D2, D3, and D4. And again, you find that the left-hand side, the integral of divergence is the sum of integrals of divergence of D1, D2, D3, and D4, because integral of scalar function has the property of additivity. And the right-hand side remains only the contribution of this external piece of boundary and internal piece. But here is one delicate thing, that here the unit normal, external unit normal, looks in this direction, and here it looks in this direction. So it is outside of domain D, but it goes to inside this hole. But this hole is external to domain D, so it is a small delicate thing. So for this domain, we have this also this theorem also holds. Yes, so in this case, left-hand side is integral over this annular domain of divergence, and then right-hand side is the sum of two integrals, integral over S1 and integral over S2. Yes, integral over this part of the boundary plus integral of this part of the boundary. And we should not forget that here the normal looks in this direction, here inside, outside of domain D, but inside this hole in domain D. Yes. Now, with this inside, we can consider another theorem, which is a little longer, but now I can explain it. The plan, how it is done, is exactly the same. It is the Green's theorem. Suppose again we have domain D with a boundary S, and we have two functions, u of x and v of x. No, for more accuracy, they are both in C2. So have continuous first and second derivatives in domain D, including up to the boundary S. And consider the following integral over D u of x times Laplacian v of x dx. And again, we have to we can transform it to the other form using the partial integration. So it is integral over d u of x times sum d to v dx I square as a function of x dx. And let us take one term, sum from I to 1 to n. Let us take one term for some I. So integral over d u of x times d to v dxi square dx. We can transform it in the following way. Again, we consider the xi axis, and here all other axes which I together denote by x prime, and we have equals integral over it is a projection on the x prime, it is say di this projection. Integral over di, integral, it is dx prime, integral from phi of x prime to psi of x prime, u of x prime xi. Yes, so I include here x, it depends on x prime, d2v dxi square dxi. And now I integrate by part, equals integral over di, no, dx prime, and here goes, we have to take, let me write it, u of x prime psi of x prime times du dxi of the point x prime psi of x prime minus u of x prime phi of x prime times du dxi of the same x prime phi of x prime. Yes. And then the same way I transform it to the following form. Equals integral over s. No, I'm sorry, I forgot minus integral from phi of x prime to psi of x prime du I dxi dv, it is v, du dxi dv dxi dxi. Yes. So we transformed it as I integrated by parts. Now I can integrate it, I can write it in the following form. Integral, the first term, integral over s u of x times dv dxi ei unit vector dot n ds. Yeah, exactly like I did in the previous theorem, in the divergence theorem, minus integral over d already. So it is integral over d scalar function du dxi dv dxi dx. And now I can take this integral integrated by parts again. Equal again integral over s u dv dxi e I dot n ds minus, again I look integral over d I, again dx prime integral from phi x prime to psi of x prime du dxi, let me write in other order, v of x prime xn du dxi plus, so if I write this, integral over di of what? V x prime xn du d2u dxi square d xn dxi, and here dx prime. And after all, we have so let me write again integral over d u d2v dxi dx equals integral over s u dv dxi ei dot n ds minus integral over s v du dxi ei dot n ds, and remains plus integral over d v d2u dxi square dx. Okay. Now if you, it is for one I, if you add for all I, then you have integral over d u times sum d2v dxi square I from 1 to n dx equals integral over s u times sum dv dxi ei dot n ds minus integral over s v times sum du dxi ei dot n ds plus integral over d v times sum d to u dxi square dx. Now we can use our advanced notations and see that. One moment. This is sum d to u dxi square I from 1 to n equals Laplacian u. Sum d to du dxi ei is a gradient u, and the same for v. And so what is written here? Integral over d u Laplacian v dx equals integral over s. It is written here u gradient v dot n ds minus integral over s v gradient u dot n ds plus integral over d v Laplacian u dx. Now, or we can move all the integrals, volume integrals over d to the left and leave the surface integral to the right and have the final formula. Final formula. So integral over d u Laplacian v minus v Laplacian u dx equal to integral over s u gradient v minus v gradient u dot n ds. This is called Green's formula. So here I repeated a section from the calculus book. If you know it already, so you know it. If you don't know, maybe it will remind you about these things. And in this lecture, I am not going to discuss what this formula, this and previous formula, what they give for the study of Laplace equation, you see that Laplacian appears in this formula already. I will do it in the next lecture. So for now, let us finish. It is such a lecture not directly related to our study. It's not the piece of our course, but it can be helpful. So keep it in mind. Have a good time. Bye.